Okay.
So, our speaker today is Mikhailo Dokuchaev, and his title, as you can see there, is Co-homology of cross products by unit interactions of inverse monoids with applications to Steinberg algebras. Please, Misha, go ahead.
Thank you, Willy, and let me start thanking for the invitation. So thanking Willy and Maria Eugenia. It's a pleasure to talk to you. So was not totally clear for me what kind of audience should be for the talk. So there will be some very elementary for those of you who already have knowledge of homological algebra. Maybe I can speak faster. I don't know who will then assist or see this recorded, maybe students or whatever. So in any case, I have some very basic things at the beginning. So this is a joint work with Mykola Khrypchenko from Florianopolis, Federal University of Santa Catarina, and Juan Jacobo Simón from a university from University of Murcia in Spain. So Florianopolis in Brazil. So this is very basic. So notation. So we have here the opposite algebra. For so far, K will be a commutative ring, but later I would wish to assume that it's a field. And this denotes the enveloping algebra. In this context, it's called enveloping algebra. The word enveloping is used for various. There are more than one meaning, right, in mathematics, but in this context, this is this tensor product. And also very easy and very well-known fact that if you have a bimodule over A, you can see it as a left module of the enveloping algebra, and also as a right module over the enveloping algebra. Well, now a Hochschild homology, for eventually those who will see this later, I don't know. So I recall here, so this is just the left the right functor of, so this is the Tor functor of the tensor product functor going out from the bimodule, the category of bimodules, and entering the K modules. And it can be computed, for example, taking projective resolution of M, then taking the deleted resolution, tensoring by A, and so the Hochschild homology is the homology of this complex, which we are going to get this way. And similarly, the Hochschild homology is the X functor. So it's the right functor of this home functor. Again, defined of the bimodules and with values in K modules. And we can compute it taking injective resolution of M, co-resolution of M, and applying the home functor to the deleted co-resolution, getting a complex, and the Hochschild homology is the homology of this complex. Now some basics on inverse semigroups. So I think I did something wrong.
We can hear you.
You can see my file?
Well, I see up to the line where it says example, I of X is always ejections between subsets of X, X is set.
Yeah, but somehow I pressed something so I cannot see the file. I'm showing.
You're showing the hand cursor, which is right beneath the line where the example of I of X is defined, and now you raised the hand up to the.
Okay, I see already. Yeah. Sorry for the
no problem.
For the error here of so I can see my file. Sorry for that. So A semigroup is called inverse if for any S there is a unique element which we denote as inverse. Many people denote as star, so it's not the real inverse, it's just like a partial inverse, so that these two equalities hold. An important example is the so-called symmetric inverse semigroup of all bijections between subsets of X, which are we call partial bijections, and the composition is defined on the largest possible domain. The importance is that any inverse semigroup is a subsemigroup of the symmetric inverse semigroup. This is an analog of Cayley's theorem. And what is important for us is the natural partial order on the elements of the inverse semigroup. So S is smaller than or equal than T if and only if S can be seen as E times T, where E is some idempotent of the semigroup. There are other equivalent conditions, but it is enough for us, I guess. An important class of inverse semigroups intensively studied by people in semigroup theory is the so-called E-unitary inverse semigroups. These are those inverse semigroups for which the idempotents form a unique sigma class. So what is the sigma class? The sigma class, if you go from T to S, you are in the same class, and if you go up to another element, you still in the same class. So this natural order defines an equivalence relation, which is a congruence actually. So it generates an equivalence relation, which is a congruence. So if all idempotents form a unique sigma class, then our semigroup is called E-unitary.
So, sorry, so sigma has nothing to do with the countability assumption.
No, this is a well-established symbol for people in semigroup theory. So let me say once again, two elements are sigma related if and only if below them there is an element. Okay. In particular, S and T are sigma related, but if above S there is some other element, that will be sigma related to T.
So it cannot have a zero element.
Well, it can, then everyone will be sigma related. It can. But you see, for I believe you think of Steinberg algebras. So this E-unitary will not be important for that case. This has another importance for semigroup case. Importance of that there is this McAllister covering theorem, which one of the important theorems involves E-unitary semigroup. So every inverse semigroup is isomorphic to a idempotent separating quotient of a E-unitary semigroup. So what is that? So it is a quotient, but this quotient doesn't glue the idempotent. So it is like an epimorphism, but the epimorphism separates the idempotent. Different idempotents go to different images. So this is one of the importance of the E-unitary semigroups. Well, now actions we can find in Excel paper. An action of an inverse semigroup on a set is just a homomorphism of this form. So this homomorphism of S into the symmetric inverse semigroup of X. Then it can be easily seen that the inverse element goes to the inverse bijection, right? So it respects inverses in this sense. In topological case, we assume that So we say that theta is an action is topological if each theta s continuous and the domain of each theta s is open in X.
Sorry.
And one can, yes?
Yeah, Rui imposes a non-degeneracy condition that the union of the domains of the theta s be the whole of X. You are not imposing.
Yeah, I am not, but I mean, for some purposes, it's really important, but I'm not imposing now.
Okay.
In general definition, I mean, at least how we use it, no, we do not impose. So this consequence that theta s is a homomorphism. Now, actions on algebras, you can find on sister case in the paper of Nandor-Zeven, and in abstract case, there is a paper of Ruexel and Felipe Vieira. So an action of an inverse semigroup on an algebra over a commutative ring is an action of S on the set A, such that each domain is a two-sided ideal of A at the domain of each theta S, right? And each theta S is an isomorphism of algebra. So it's an isomorphism between the ideals. Okay. We will assume that S is a monoid. It's an inverse monoid. So we wish to have identity element. And the action theta is unital, which means that each that it respects the identity element, first of all, and moreover that each range theta s is a unital ideal, a unital algebra, so it's an ideal generated by an idempotent which is central in A. Now, we want to define what is the cross product. It is done in two steps. So let's suppose we have an action, a unital action, and we form this L, which is the direct sum, external direct sum of these ideals 1s A. So these 1s are the generators of the involved ideals, right? And delta S is just placeholders, just a formal symbol. This external direct sum of these ideals 1s A. And the multiplication is as expected. So we multiply A delta S by B delta T. And so theta S would act on B. Since B may not be in the domain, then we put it into the domain by multiplying by the generator of the domain, right, by this item. So then it falls into the ideal, which is the domain of theta S. So it turns out it's not really that definition is satisfactory. For example, in group case, it would be okay. But in the case of inverse semigroups, there are redundancies which are needed to be removed. So what is the redundancy? So this difference is a redundancy. You have the same A, the same coefficient A, and S is less than equal than T. So we take the ideal generated by this set of redundancies and we factor out. That gives some difficulty, maybe inconvenience in the definition of the cross product. So the cross product by theta is this quotient, but this is the definition which fits nicely representation theory. So our purpose is to speak about the homology and cohomology of this cross product. And for that, we need also homology and cohomology of S. So there is a well-known homology theory of inverse semigroups made by Hans Lausch, but that is not what we need, because in that homology, the modules are commutative inverse semigroups. So, and the inverse semigroup S would act on them and with some certain restrictions. So this is not what we need. So we define a different homology. I don't know if it was defined before somewhere, so I didn't see. So we denote by ES the set of all idempotent elements of S. Then we have this subalgebra generated by, so the semigroup algebra KS is just the free module over K whose base is in S, right? That's all finite combinations of elements of the semigroups with coefficients in K. Then we have this subalgebra generated by the idempotence. So the basis here is the idempotence of S. And we consider a left action of Ks and the right action. So it becomes a left module and the right module over Ks. So we want these actions. And these actions are given by conjugation. So this is the left action, and this is the right action. Now we define the homology and cohomology. So we take any module over Ks, any left module, and the homology then will be the store function. So this will be the homology of S with values in F, in V. So you see that here we take this K ES. So it can be seen as augmented homology, right? That is an augmented ring and the known concept of augmented homology. And similarly, we take the cohomology. So this will be X. Here we again have this KES. And so this will be the M cohomology of S with values in V. So these are our definitions. So let me say a few words about these things. Tor and X can be computed taking projective resolution on first variables. So we produce a projective resolution. So here is the notation. This DS is usual notation in semigroup, in inverse semigroup theory. So this we call domain of S. If you look the inverse semigroup inside of the symmetric inverse semigroup, if you think them as partial bijections, meaning bijection between subset, so this is really going to be the domain of that partial bijection, and R is going to be is missing S here. Sorry, S should be S between parentheses in brackets. So this is going to be the range. And now we define the following projective modules. So it is well known that these are idempotents and can be immediately seen from the definition of inverse semigroup and its inverse, right? So these and domain and range are idempotents. In the symmetric inverse semigroup, the idempotents are the identity bijections defined on subsets. Now, here you see this idempotent. So this is going to be a projective module, right? There's a sum of these guys, where S run over all elements of S. And we would like to have a convenient notation in order to have formulas which would work like bar resolution for groups, right? So the notation is the following. So we can show that Pn is isomorphic to the following free K module, whose basis is formed by these elements here. T and between brackets S1, so on Sn, but the domain of T should be below the range of this product. So this restriction we impose, and then one can check that this free K module is isomorphic to to Pn for n bigger than 0. And if n is 0, then we just write T and this empty bracket. So this is going to be this free K module. Then we can define this homomorphism, which look like you get in bar resolution. So that, but the idempotents show up. So you see here you have the range of S. And of course, in this context, we always have that restrictions that the domain of S is below the range of the product, right? But this formula is look like in the bar resolution. So it's very familiar formulas, essentially, but put in our context. So the sequence is a projective resolution of this KES in the category of left KS modules. And also we have a similar projective resolution of KES in the category of right KS modules. Well, given a left KS module, let me speak about cochains. And speak about chains, cochains, so I don't want to put too many formulas, so let me just put cochains. And again, you will see familiar formulas, but you see the cochain has values in this submodule. So here you see that this idempotent, this range of this product appears again. In delta 0 appears the range, and also in delta n the range. So if you ignore the range, this is just the usual formula which you see in the case of groups. Very familiar formulas, well, essentially, but not with this detail, right? And this sequence then is going to be a cochain complex whose cohomology. So this will give the cohomology. Analogously, we are going to have, we also have for homology. So the nth cohomology of this cochain complex is isomorphic to that cohomology which we define. And we can define, given a left KS module, we naturally define the Zn as the kernel of delta n, Bn as the image of delta n minus 1. And then we are going to have that our zero cohomology group is just Z0, and n cohomology is just this quotient of cocycles by boundaries. And for low cohomology, you can also see formulas which are rather similar to usual formulas which you have for groups, but idempotents show up. So Sx will not give X, but Rsx. So the idempotents, the range of S appears here. Here, for the one cocycle, the range St appears here, but if you ignore this, it's just the usual formula for one cocycle. The one boundaries, in one boundaries, again, you have this idempotence, and in two cocycles, again, appears this idempotent, and so on. And two boundaries again. So these are familiar formulas, but with idempotence, appropriate idempotence incorporated in them. We have similar formulas for homology. Now, in order to mount, to build up the spectral sequence, I can say a few words how does it do, but I will show, don't show the details. But suppose you have a unital action, and then we need to transform A into left KS module, and it is done this way. So just by the action, this action of theta s, you multiply A by 1s minus 1 in order to put A into the appropriate domain. And now take a bimodule over the cross product, and we transform it into left KS module this way. So of course this needs a calculation. And we also transform it into right case module by the symmetric formula. So with a bimodule, we have a left KS section and the right KS section on that. Also, M is an A bimodule. This is quite natural. In that cross product, we can, there is a canonical map of A into the cross product, just taking the class of A delta 1. And also it can be shown that it's an immersion of A, right? This also needs some computation because we are cutting by an ideal, right? But we can show that A is embedded into the cross product. And so this is the copy of A inside of the cross product acting on M. We also need action on tensor product. So we tensor M by A, and it's going to be to have a left case module structure, and S will act on both, on A and on X. As we mentioned already, A and M have left case module structures. And for cohomology, we will need the left case module structure on AM. And so and it is given by this formula. So we'll multiply A, we act on A by S inverse, apply F, and then act by S. So it's kind of conjugation of F, right? And so our result for spectral sequence is as follows. Here I will assume that K is a field. And we also assume that the enveloping algebra of the cross product is flat over the enveloping algebra of A. Actually, first we prove it without this assumption, but then we what we can get here is the left-the-right functor of certain functor of the tensor product functor, certain tensor product functor. But in order to identify it with the Hochschild homology, we need this this restriction. So we assume that this is going to be flat over over the enveloping algebra of A. Then we have a first quadrant homology spectral sequence converging to the Hochschild homology of the cross product. It involves this homology of S defined like we defined with values in the Hochschild homology of A. And also in cohomology case, we assume that this enveloping algebra of the cross product is flat as a right module over the enveloping algebra of A. If we don't assume this, we still have a spectral sequence, but in general, we are not able to identify it with the Hochschild homology. It will be the right functor of some functor, right? Some home functor. But in order to identify it with Hochschild homology, we need this flatness condition. And then we have a third quadrant cohomology spectral sequence converging to the Hochschild cohomology of the cross product with values M. So it involves the cohomology of S with values in the Hochschild cohomology of A with values in M.
One question, comment. If in the particular example where, say, A is the algebra of locally constant compactly supported functions on a space, on a locally compact Hausdorff totally disconnected space, then and S acts on the space, then the cross product algebra is the Steinberg algebra of the transformation groupoid corresponding to the action of the semigroup on the space, right? So on the right-hand side, you have Hochschild homology the of the groupoid algebra with coefficients in M.
Yeah.
Now, this in particular A, if I'm not mistaken, is a colimit, filtering colimit of separable algebras over the field K. It's
it will collapse. It will collapse this.
It will collapse. Yeah.
I will show you.
Yeah. Okay. So that
you know already.
Yeah. No. That surprised me that it collapsed. Okay.
Yeah. But we will not explain it via
sorry
separable
for going
algebras.
ahead. Yeah.
What you are saying is okay. Our explanation was different, but it collapsed. But looking at separable case, because the separable case is collapsing also. I will mention it actually, the separable case, separately, just an example. But when I will apply this to Steinberg algebra, then in homology case is going to collapse. In cohomology, okay, let me think. In cohomology, maybe your explanation is better.
Yeah, well, maybe. In cohomology you have a problem because the colimit doesn't go well product with cohomology.
Yeah, cohomology. Yeah, in homology it will be nice. So I will get there. Maybe we can speak more about that. Let me, but this is very pertinent observation. It's at the point, of course. Now, assume that S is E-unitary. Then we prove that it is flat. This is a non-trivial fact. It is flat over this enveloping algebra is flat over the enveloping algebra. So it's not immediate. So it's a proposition, but it needs some calculations. So then it's automatic. So in case of it's flat left and from the left and from the right. So both of these sequences work for the case of if S is E-unitary. Then this flatness condition is automatic, is guaranteed. We prove that. Okay. Now, separable case you mentioned. Separable case collapses, and the flatness condition is guaranteed in separable case also. So it collapses on p-axis, the spectral sequence. So we have this isomorphic. So the Hochschild homology and is isomorphic to this homology of S with values this module of coinvariance. Maybe we should call it like coinvariance, right? Then one can show it's quite known that this is the zero homology, but in our case, it also we need isomorphism of KS modules, but it's also works. So AM is just spans a non-notation. It's just a linear span of AX minus XA, right? In cohomology, we also have collapsion. In separable case, in cohomology, but in this case, we have the submodule of invariance, right? So again, we show that this is well known that it's zero cohomology, but in our case, it should be isomorphic as KS modules, but this works easily. Okay, so these are the modules, submodule of invariance, right? So this is the separable case. Now, let me recall, I don't know, maybe maybe all of you know very well, but I don't know, maybe people who will look at this talk, or maybe students, I don't know. So I recall some very basic things about Steinberg algebras, right? So a groupoid is a small category in which any morphism is isomorphism. G0 denotes the set of unit elements. So these are the set of the groupoid. There is a source map, right? We have the range map also. And important notion is a bisection. So a subset of the groupoid is called a bisection if the restriction of S on U and the range map also on U is both restrictions are injective, right? Okay, an étal groupoid is a topological groupoid whose unit space is locally compact in Hausdorff in the relative topology, and the range map is a local homology. Well, then it is a consequence that the source map is also a local homomorphism, and they are open maps like all local homomorphisms. A topological groupoid is a groupoid which has topology such that the multiplication and the inversion are continuous on the appropriately considered domains in the relative topology. An étal groupoid is called ample if the topology admits a basis formed by compact and open bisections. Now, taking two open compact bisections, it is known that the product is again a compact open bisection, and the inverse, this point-point inverse, also is a compact open bisections. And moreover, the set of all compact open bisections form an inverse monoid of the ample groupoid G. This is also true for étal groupoids, but I will concentrate on ample. So this A stands for the ample case, but if you remove A, the notation will refer to étal groupoids in general, but I'm not going to use that.
So are you assuming that the unit space is compact?
I will assume.
Okay, because you are
assume.
that
for these definitions, of course, I don't need, but I will assume because we work with usual homology of unital rings, and
because you wrote
one should think of non-unital case, of course, but we did for unital. So I will assume, I will assume. But before doing that, we have some more definitions. So if you take an open compact bisection, then you define this map theta U, defined on the domain of U and with values on the range of the U, and it's just send any x from the domain to the range of gamma. Since U is a bisection, for any x there is a unique gamma such that gamma is applicable to x. So the unique gamma whose domain is x, right? Better to say it. So it's very natural action. And if you consider all theta U, where U runs over all compact open bisections, then it is we get a topological action of theta on topological action theta of this inverse monoid on the unit space. This is known facts, and let us write the domain of U will be x indexed by S inverse, and range of U x indexed by S. This fits the usual notation of action of an inverse semigroup on a set or a topological space. So small s is just a compact open bisection now. Now we assume that X is compact. Let K be a field, then Lx is that algebra of continuous functions which you mentioned already. Now, continuous is the same as locally constant. And K is considered as discrete topology. Then if you put on K the discrete topology, then you locally constant is the same as continuous. Now that action of S on X induces an action of S on the locally constant functions in a very natural way. So we denote this action by theta hat. So you take a function f from here, so locally constant function defined on X S inverse, and you want to get a function which would be defined on X, capital X sub S. So what you do, you take theta S inverse, which will map capital X indexed by S to capital X indexed by S inverse, and then apply this a very natural and usual definition which shows up, right? And then theta hat S is an isomorphism for algebras, and all the collection of all theta hat S is a unital action of S. I denote by S now this inverse monoid of compact opal bisections, okay? So we are going to have a unital action of S on the locally constant functions. Another known fact, so let's recall what's the Steinberg algebra. So we take an ample groupoid, which is not necessarily Hausdorff, but we have a compact unit space. We assume that it's compact. Then we take the span of all characteristic functions of compact open subsets. So we'll take the linear span of that, and we define the convolution product. Another way is define them on this characteristic functions. So the convolution product of two characteristic functions of locally compact, compact open bisections will be again a characteristic functions of the product of the product of that compact open bisections. So this is the Steinberg algebra, and then the locally constant functions form a subalgebra, and that it is known that the Steinberg algebra is a cross product by the action theta hat. So in sister case, you can see it in the paper by Axel in Bulletin of Brazilian Mathematical Society 2008. It appeared in purely algebraic context in the PhD thesis of Paulinho de Meneghi, a student of Axel. Also, he published then in 2019 in Advances of Mathematics. And also it appears in the paper by Daniel Gonçalves and maybe Viviane Beuter. So this is a known fact, and we are going to use that fact. So this is our result for the Steinberg algebra. So you see that what happens, it is not written here, but what happens is that the spectral sequence collapses because those homology groups which appear inside of the spectral sequence. Our explanation is that these locally constant functions, they are generated by idempotence, and any commutative algebra generated by idempotence is Von regular. Then it implies that the enveloping algebra is also generated by idempotence and also Von regular. And we know that any module over von Neumann regular ring is flat, and that flatness collapses the sequence. So it's collapsed on p-axis, and that means that we have explicit isomorphism. For homology, we don't know. we just call, so this is just the spectral sequence what we had for semigroups. So we just explained that, well, one thing which needs to explain that flatness condition of the enveloping algebra of the cross product over the enveloping algebra of the locally contact function, but that works. And therefore the spectral sequence applies for the Steinberg algebra. Now the way, so now we are 10:51, maybe I should stop, but if you want to know something, how we prove, I can say a few words.
I want to ask something. So, can I take a semigroup that is smaller than the whole semigroup of bisections, like for anyone that is a basis for the topology of G? Because I'm thinking, I mean, you start with an inverse semigroup that acts on a space X, and then you form the transformation groupoid, the Jan groupoid, as Rui calls it. And this will have, so the original S will provide slices or bisections for this groupoid, and will provide the basis of them, but they will not be all of them. So I wonder, I mean, I think that in the cross product, it's the same.
So you think we have too much bisections?
I think you do not need all of them. I mean, at least you do not need all of them for the. I mean, to say strictly what I know, because it's in Rui's paper. So you start with X, with an action of S on X, okay? Then you form a groupoid, and you can. This groupoid has a unit space, and once you have an étal groupoid, you have, if you take any subsemigroup of the semigroup of all slices, that is a basis for the topology, and you take the Jan groupoid for the action of this subsemigroup on the unit space, you get back the original groupoid. You can do that.
That should imply, I think you are right.
So because so that if you start, because I mean, if your groupoid comes out of an action of a given S on X, you want that X you started with to appear, not a bigger one, I suppose.
Yeah.
But also one thing that I find surprising is that, so say if M is just L of X, then since L of X is commutative, this commutator quotient is just L of X.
Yes.
So we are saying that, no. Okay, yeah, to get Hochschild homology with M, we should get M, to get the usual, to get Hochschild homology of the algebra coefficients in itself, M should be the algebra coefficients in itself. Okay.
So no, you could take M the Steinberg algebra, right?
Yeah, but then on the right hand side, you get you get something. Another thing, at the beginning, in the discussion we had before we started the talk, you said that you were sure that this semigroup homology should be the same as groupoid homology for the universal groupoid or the semigroup. I think it is the same because the Steinberg algebra of the universal groupoid by Steinberg's result is the same as the semigroup algebra.
Yeah.
So modules are the same and the tors are the same. So, right? I mean, that's just by
Okay.
the categories of
Okay.
modules are the same. They're the same algebra. So, okay. Yeah,
That should be same. Yeah.
that's what I. And you wanted to say something. I suppose it's about the proof. I suppose it's some application of the Grothendieck spectral sequence.
Yeah, of course. Just the appropriate functors, but there is a work with those functors. So
yeah, I suppose that I mean the whole thing is to prove that you are in the
conditions.
in the conditions, right? Yeah.
So we apply two of Grothendieck theorems, and one we use for homology, another one for cohomology, and with appropriate functors. So I think I cannot write, so maybe no need to. I could say by words which functions, but I mean, for homology, the first function is just tensoring by A. I'm speaking about that general context, right? We have an action on A. We tensor on A over the enveloping algebra. This is the first function. But we apply it to the bimodules over the cross product. So it's not really immediately the Hochschild homology, right? And then the result is going to be KS module. And then for KS module, we take another function with tensoring by KES, that capital ES, that subalgebra generated by idempotence. And we tensor by that over KS, and this is the second functor. And then we show that this functor satisfies the Grothendieck condition, but then we need to identify the composition with Hochschild homology, and that needs some work. And but this is also proved under the conditions we consider. And then another theorem for Hochschild homology that we take appropriate home functors, right? Appropriate home functors, and also some work with the functors, work with functors and so on using some homological algebra. Okay, so thank you. And thanks you, Willie, for your comment about groupoids and other comments.
Yeah, thank you for the very nice talk. Yeah, I just saw. Okay, so are there any questions from the audience? Okay, otherwise, but the Varshi, my co-author, says, would you ask him how our results, how their results compare with ours? But I don't know if you know ours.
I saw the paper. You are referring to Steinberg algebra, right?
Yes, yes.
So far, very briefly to understand if there are intersections or not. That was my first.
One thing I thought is, I mean, we show that in the case when the groupoid is Hausdorff,
yeah,
the groupoid homology with coefficients in
the algebra.
In the algebra of the unit space is a direct summand of the Hochschild homology of the whole algebra.
Yeah.
Now, perhaps from your result, I mean, if you can start, since you know this is already groupoid homology with coefficients in some module, maybe by showing that this module splits into the direct sum of two modules of two modules, then that you get that this is split indirectly.
That's interesting. Yeah, interesting question.
But yeah, I also wonder because whether your point of view simplifies the calculation, the problems we had to establish in a general the Bulgaria type decomposition, at least under some assumptions. In general, you do not expect it to hold because, I mean, there is a topology which is non-trivial. Yeah. But yeah, it's I think it's very, very interesting, and we should look more into each other's papers to see how to combine these things.
Yeah, at some moment I will need to look.
Yeah.
At this moment, I'm just late with some other co-authors or things, but
Yeah, I see.
definitely this groupoid view should be considered. Maybe we should exchange some messages on that.
Okay, great.
At some moment.
Yeah, sure. Okay, so I'll let you know if we make some further progress along these lines.
Oh, thanks a lot. Thanks in advance.
Okay, so it's been a pleasure.
Equally.
It's been a pleasure. Bye-bye.
Bye-bye. Thank you. Bye-bye.